This work began a few years ago, actually, when I was on sabbatical in the US. It started when I was at Illinois, when these guys, David Fow and James Spencer from DeepMind, which is a machine learning company in London that was acquired by Google, it's now owned by Google, and they were working there. They came to me because they were thinking about using neural networks to represent wave functions. And that was after Carleo's work on lattice models, but before really almost anything else had been done, before anything had really been done on continuum systems, or almost anything had been done on continuum systems. David is actually an American with a degree in physics from Stanford, and James is British chemist with a degree from Cambridge. They both have PhDs. At the beginning of the project, Alex Matthews was also working with us. He's now moved on to other things. He's also at DeepMind, and Alex Botev has worked a little bit with us. I've never actually met him, though. He's DeepMind's kind of optimization expert. So he really wrote the optimization code we use. It's called KFAC. These are two PhD students of mine who started in the middle of COVID a year and a half ago. They're both working directly on FermiNet. And then Wantong Lu is a new PhD student who's just started this year, who's also doing machine learning, but not actually involved with FermiNet in this project, and that's me. So really, all the work I'm going to talk to you about, the real work, has been done by David and James, Gino and Halvard. I have had people sort of naturally assume, because I've been doing quantum Monte Carlo for years, that most of the ideas in this were mine. That is not true. Nearly all the ideas in this were David and James's, actually. I had a few of the ideas later on, but they did everything. And you'll soon see that my knowledge of neural networks is quite limited, let's put it that way. I just thought I'd start with an introduction. We had a nice one yesterday, and this will be, for that reason, I'm going to keep this one shorter, but there's a couple of different viewpoints I wanted to bring out. As Jan said yesterday, we're interested in solving the many-electron Schrödinger equation, and here's the Hamiltonian. We can work in the Born-Oppenheimer approximation almost always, so the nuclear positions are fixed, but we still have the electronic kinetic energy. If we could solve that, we could, in a sort of silly reductive way, understand in principle almost everything in this room. In practice, I don't think that's really a useful approach, but in principle, that's true. This problem is known to be NP hard, and I was told a couple of days ago it's even worse than that. So the best we can realistically hope for are approximate results. There's no point in reasonably sized systems of trying to get exact results here. And the other problem is that for room temperature chemistry, which would be nice to be able to do, KT is 25 millivolts. So we need energy differences to order this energy scale. Chemists talk about chemical accuracy, which is 1 kilocalorie per mole, which is actually 43 millivolts per particle. We'll be working mostly in Hartrees, so it's 1.6 millihartrees. So try and remember that number. That's the kind of accuracy you would want to aim at for chemistry. A drawback of this is that if we just take the Schrödinger equation and we calculate a many-electron eigenstate for a small atom, it's well over 100 eV. It's often 10,000 eV if there are some core electrons around. So chemical bonding energies are a few eV, chemical reaction energies might be a tenth of an eV, and correlation effects are often much lower than that again. And so we're solving an equation whose natural energy scale is the Hartree, 27 eV, and whose ground state energy might be tens of thousands of eV, and we're after stuff down at the tenth of an eV level, which means yes, we can only get approximate solutions, but they unfortunately have to be good ones. It's a tough problem. One thing that's not often pointed out, but because I'm really a condensed matter physicist, not a quantum chemist, if you're doing solids and you want an accuracy of 0.1 eV, that says that if you say the Fermi energy is 10 eV, that means E over E Fermi is 10 to the minus 2. And just by dimensions, that means the wavelength, the natural wavelength corresponding to this over lambda Fermi is about 10. And if you put in some numbers, that gives you 20 angstroms. So you need to be able to consider waves with length scales of about 20 angstroms. And unfortunately, that means you need big cells. And this is the root of all the problems we have with, well, one of the roots of all the problems we have with size errors. When you're trying to do quantum Monte Carlo methods or any many-body method for solid-state systems, you have to make your simulation cells big to get the right answer, but you can't make your simulation cell big because it's too expensive. So it's one of the reasons solids are so hard. Okay, next slide. Of course, you can do DFT. I really like DFT, and it can sometimes achieve chemical accuracy, but only if you choose the right functional, and it doesn't really tell you how to do that. And in particular, most of the functionals are parameterized on sort of electron gas physics, and if you now go and look at a strongly correlated system which is not like a Fermi gas, goodness knows how they'll work. It's very hard to know in advance. You can do perturbation theory, GW, for example, and beta sub eta, things like that. They suffer from the same problems. What about strong correlations and non-Fermi liquid states? Or you can do the silliest thing you could imagine, which is to guess the wave function, which is the basis of really most of the quantum Monte Carlo methods. It seems idiotic, but if you look back at the few interesting many-body problems that have ever been truly solved, many of them were solved by guessing the wave function. These are three famous examples. Yeah. How Bob Laughlin, not far from here, I guess, wrote down the wave function for the fractional quantum Hall effect. To me, it's still black magic. I just don't know how he did it. But anyway, it's not as... All I'm trying to point out is, although it seems an idiotic thing to do, we're trying to guess a function of thousands of variables. It's not as idiotic as you might imagine. And it's the basis of many of the methods one uses to study interacting quantum systems. From Hartree-Fock, that's a guessed wave function. CI is a kind of expansion in determinants. That's a guess, really, if you truncate it. Almost all of these things, if you view them in one way at least, can be regarded as kinds of guessing the wave function. They're parameterized guesses. They may have thousands of parameters that you optimize, but they're all really guess the wave function and optimize it. And Fermi Net, which is what I'm talking about today, very like Pauli Net that Jan talked about yesterday, is just another one of these. Yeah. Depends how you look at RPA. If you look at it in the old Bohm-Pines way, they explicitly write down a wave function which is some electrons multiplied by some plasmons. So yes, you can regard it that way. If you think of it as in diagrams, it doesn't look like that. So it's a matter of viewpoint. But I would argue yes. I don't think it matters very much. So what we're doing is guessing the wave function. And I thought I'd go back and look at the kinds of guesses that appear mostly in simple quantum Monte Carlo methods, specially used for solids. So I'm talking about variational and diffusion Monte Carlo. The simplest wave function you can look at is a Slater determinant multiplied by something, some kind of factor, that's supposed to reduce the value of the wave function whenever pairs of electrons get close together. That's the simplest thing you can imagine. This is called a Jastrow factor. And of course, you can have a vast linear combination of determinants and a much more complicated thing in here. And you can extend this, but this is still really the root of much of the quantum Monte Carlo stuff for large systems. Whoops, wrong button. If you use a trial wave function of this type, you can't usually get chemical accuracy. And if it doesn't work, what do you do next? You can fancify the Jastrow factor and try out. You can make the Jastrow factor better. That's limited. It can get you somewhere, but not everywhere. You can use linear combinations of determinants, but like Brian Clark, I'm a bit down on that. We do it, but I'm down on it because it scales sillily, at least in general. And if the Fermi liquid physics is very wrong, you don't know what to do. And yeah, I don't like linear combinations of determinants. In principle, of course, that works. So where we start to try and understand Fermi Net, the ansatz we're using, which is just a different kind of wave function, is from a Slater determinant. This is not how we got at it. In fact, David got at this, the ansatz we use, by starting with a neural network and thinking, how can I write down a neural network which is properly antisymmetric? What can I do architecturally inside a neural network? And so that's how we actually got at it. But what he ended up doing is what I'm about to describe. So let's take a Slater determinant. You don't actually require the things here, the entries, all to be functions of the coordinates of a single electron. The only requirement, I think, was it Brian said this earlier? Somebody said it, is that if you interchange two electrons, for example, R2 and R1, you flip two columns and therefore change the sign of the determinant. That's all you need. And that allows you a lot of freedom to put more interesting things inside. And what we're putting inside is, we still think of them as orbitals, and it's still psi I of Rj, so this is psi 1 of R1, psi 1 of R2, psi 1 of Rn, just as it was before. But as well as depending on Rj, this orbital, we call it a Fermi Net orbital, depends on the positions of all the other electrons. Okay? The only constraint is that the way it depends on all these other positions must be completely symmetric. If I flip around any pair of electrons in this list here, the wave function doesn't change value. So it's like they've turned into bosons almost. So we think of it then as the wave function is a function of a particular R and the set of all the other R's, and it's an unordered set. It doesn't matter which order they come in. And here's a determinant made like that. And I think I was going to say a couple of things about this. You might ask, how restricted is a wave function of this form? Is it in principle possible to represent any many-particle wave function in this form? The obvious answer is no. I believe the correct answer is yes. With one of these, you can in principle represent any many-particle wave function. We have an argument in our paper that sort of explains this. It's quite a subtle one, and I still sometimes doubt it, but I think the answer is yes. And the way the argument works is you start with an arbitrary many-electron wave function, and from it construct something that looks like this, that is the same thing. I don't want to try and explain it now, it's complicated. That's a completely different question from, are the entries in here simple enough that we could represent them with a reasonable neural network? The answer to that one is well, to some degree, yes, but not perfectly, of course. So I just wanted to show that this thing is properly antisymmetric. And you just do it with an example. So here's one of these things, and I'm going to, I think I've decided to exchange R2 and R4. So we would like column 2 and column 4 to flip when we do that. Yeah, then this would be antisymmetric. The only issue is that the set R01 contains R2 and R4, so they get flipped around, and the set R03 contains them. So these columns also depend on R2 and R4. I just colored them to show what's going to happen, and I'm going to start looking at the things in those columns and see what happens to them when I flip R2 and R4. So consider the set R01, which appears in the first column here, because it contains R2 and R4. It goes from R2, R3, R4 to R4, R3, R2, which is of course the same because it's an unordered set. So the set R01 maps onto itself. The set R02, where we flip 2 and 4, that maps onto the set R04. So this bit of this column is indeed flipping with this bit of that column, which is nice. R03 is unchanged, just as R01 was, and R04 maps onto R02. So it is genuinely true that any determinant of this type is antisymmetric. I think I've got one more picture that shows you what it becomes when we do it, when we do that flip. People often say this is backflow. It's kind of like backflow, but it goes a long way beyond backflow. In backflow, you have an ordinary Slater determinant with one three-dimensional variable as the argument of each of these wave functions. But that particular three-dimensional vector depends not only on the position of the electron you're interested in, but in the positions of the others. So you map this 3n-dimensional function back down onto a three-dimensional function as the last step. And we're not quite doing that here. So I think it's actually some way beyond backflow. Even a sort of ideal normal backflow would not reproduce this. So it's antisymmetric. And all we're doing with Fermi-Net is essentially building functions of this type, determinants of this type, and optimizing them. So the wave function the neural network is the wave function. We put in the positions of the electrons. The number that comes out are lots of numbers come out, one for each function that goes into the determinant. Okay, so we're just mapping sets of electron positions onto these functions. There's prior work that's related. The backflow idea goes back a long way. The first neural network used for lattice models was by Carleo and Troyer, at least the first I know about, and that's what started us going. That's a very, very nice, very innovative thing to do. At the beginning, we didn't realize that what we were doing was very closely related to Brian Clark and Luo's work, and I should have known this because I had talked to Brian about it. And because it was a lattice model, it just kind of went out of my head because I was doing continuum models. But it is very closely related to neural network backflow, which predates us. And it's also quite closely related to iterated backflow, which is an idea by Ruggeri, Moroni, and Holtzman. We did know about that one. We did realize that link. So here's what we do. It's just really straightforward variational quantum Monte Carlo. In go some electron positions. We have a neural network, which I won't describe the architecture, but we could talk about it later if you want. And the output layer is a wave function. So actually, there's a layer in here where we construct all those Fermi Net orbitals, and the final step is to evaluate the determinant of them. Okay? We don't put any chemistry in. We don't, usually anyway, we don't pre-train to Hartree-Fock or anything like that. We don't insist that one determinant has these orbitals occupied and another determinant has those orbitals occupied. We just let the optimizer take care of that. Once we've got, so we choose an initial neural network, which is usually random these days. We put in the electron positions, out comes a value of the wave function squared, and now we use Metropolis to sample it and evaluate the expectation value of the energy for that wave function that the network currently represents. And then we update it, but according to the variational principle, we update the network parameters to lower the energy. That's all it is. And because it's a neural network, we can do backpropagation and all those tricks to evaluate derivatives of things efficiently. But the techniques are straightforward VMC. One little problem is that we explicitly build the network to construct a smooth differentiable function of its inputs. We like that because if you have a wave function with cusps, I don't know, in 1D, if I have a wave function that looks like this, there's a cusp there, and if you integrate del squared psi over the region, I think you get a finite value from the delta function that arises from that cusp. You miss that when you're doing Monte Carlo sampling, so you actually get the wrong answer if your wave function has cusps in. So you can do anyway, but the real wave functions do have cusps, and we know what, so it's good that our neural networks are completely differentiable. There's no problem, we're not going to miss anything when we differentiate them. But real wave functions, unfortunately, do have cusps. This is a helium atom, and here's an electron approaching the nucleus, and there's a little tiny cusp here. You can probably see where an electron goes past another electron. So this is just a one-electron wave function for a helium atom. And so what we do, how do we then allow a smooth network to represent something with cusps in? We build the cusps in before we start. So inputs to the network include the moduli of the separations of the particles. So this is an electron-nucleus separation. This is an electron-electron separation. So we put those in. These have cusps in them because of the modulus sign. And then a smooth function of those can represent the cusps we want. And the network then learns the cusps. We don't like this. We've thought many times, you know how to build the cusps in analytically with Jastrow factors and things. And we've tried that again and again. And every time this is better. I don't understand why. Yeah, that's what FermiNet looks like. Blah. Yeah. Okay. David, yeah.
Could it be that the actual phase space around the cusp in 3 dimensions is negligible, right?
Yeah.
And so it would rather spend its times on part of phase space that are important.
That's something like that, I think, yeah. But if we put in the cusps, it doesn't have to worry about that region at all. It's just, it can then fit a smooth function.
But then it kind of constrains it in some way.
It could be that we just haven't done it right as well. You know, these things are very temperamental. I don't like working with neural networks. They're really awkward things. So this is we use something called KFAC, which is an optimization method that the people from DeepMind knew from the neural network community. And as you can see in this particular example, I don't remember what it was now, it's vastly more efficient than a better known Adam optimizer. Once we started using this thing, and then we thought about it hard, and we realized it's actually essentially an approximation to stochastic reconfiguration. So we're also using stochastic reconfiguration. It's an approximation designed to stop you having to invert such a big matrix. It's a kind of neural network-based approximation. And there are other ways of doing it. There's one from Berkeley, from Eric Neuskermann's group, which uses conjugate gradients, which we probably ought to try, because this one does seem to have occasional cases where we run into optimization trouble, which could be caused by the approximations we make to stochastic reconfiguration. We're not sure. Okay, and the rest of this talk's just going to be results. I don't have a time of oh yeah, okay, good. All right. Yeah, the rest of the talk's just going to be results. Lots of results. Most of them old, a few new ones. So we'll go right back to the beginning and look at atoms. This was the first thing we did. And what we're seeing on this graph is just 4 conventional Slater-Jastrow VMC calculations. The ones marked Seth here, so this sort of teal one and this brownish one, orangey brown one here, were done by Priyanka Seth from the Cambridge group. So they were done with the Casino Monte Carlo code, and they were done very carefully. Okay, it was a while ago now, but she did a good job on that. And you can see that gives you these two energies. The first thing we did is to see where you can build a neural network to represent any function you want. So we can build a neural network to represent a Slater-Jastrow function of the conventional type and a Slater-Jastrow backflow function of the conventional type. And we did that. Well, James Spencer did that. I couldn't do any of this. And optimized it and got slightly better results than Priyanka, but very consistent with hers, which is exactly what you'd expect. We're just seeing the enhanced representational capacity of the network. It's less restricted than the functional forms Priyanka had to choose. And then we did a Fermi Net, one Fermi Net determinant. This is all one determinant, I think. And it was down here. So it's gone from, say, this is a conventional Slater-Jastrow backflow, and it's reduced the errors by maybe 25% to maybe a quarter of what they were. It's much more expensive, unfortunately. This little tiny grey bar, which you can barely see at the bottom, is chemical accuracy. So we are not at chemical accuracy here. With one determinant, we're not at chemical accuracy. And no matter how we try, we didn't get there. So the next thing to do, despite my aversion to the idea, was to add determinants. So we started adding determinants. We've never gone very high, and almost all the results I will show you in the rest of this talk have been done with 16 determinants. So 16 completely independent determinants. We don't even insist they're orthogonal or anything. And what we're seeing results here are results for two molecules, carbon monoxide and nitrogen, using all with network wave functions, but one is Slater-Jastrow. One is Slater-Jastrow. Let's just look at the bluish ones. That's carbon monoxide, Slater-Jastrow, Slater-Jastrow blackflow, and Fermi Net. So here's Slater-Jastrow. Here's what you get with backflow, and here's what you get with Fermi Net. So it's similarly a similar convergence with the number of determinants, but it does appear that it's getting flat quite fast. And this is something someone else pointed out earlier in this meeting. I think it might have been Brian, that we don't seem to need to go to vast numbers of determinants. So we never have, let's put it that way. We've never gone past, well, 32-ish is the maximum we've ever looked at. The other thing we found is that it's substantially easier to optimize than just the Slater-Jastrow net, surprisingly. You put the full Fermi net in, and it's easier to do the neural network. Yeah?
The shaded region is the chemical accuracy?
Yeah, again, chemical accuracy.
So you're not able to push it to chemical accuracy below that?
We can push it to chemical accuracy, yes.
It's like still above, it's become quite flat.
Yeah, it's still above it, yes. You'll see later how we do. But yeah, it's quite hard to really get there.
I think the last statement depends very much on the details.
It does, yeah.
Neural network, and we don't completely understand that yet, but we use Adam with PolyNet, and it works really well with this art.
Yeah. Yeah, the choice of optimizer does depend on, yeah.
Helping there.
But I think I understand intuitively why stochastic reconfiguration is better than gradient descent, than ordinary gradient. It's kind of natural gradient descent is better than ordinary gradient.
So it's not for us. We've tried
yeah, okay. Well, it is for us, yeah.
It's a combination of many things.
Yeah. So, all right, it's a mystery, I don't know. But so here's 16. So here we are getting chemical accuracy. These are for atoms, and now we're using 16 determinants for atoms. This is the Fermi Net results, I believe. And these are all kinds of different things: coupled cluster, variational Monte Carlo, diffusion Monte Carlo, all done carefully. They're good ones. And so we're actually, at least for these atoms, we're doing really quite well. I think E exact was taken from something that isn't exact, I think. Yeah, it was this paper, I tried to look at it actually yesterday. It's really complicated, kind of taking experimental results and taking things away from them. So I think it's just that. We then tried adding and removing electrons. That works well. These are error bars for various atoms where we're doing electron affinities and ionization potentials. Where the affinity is missing, it's either because the electron doesn't bind or because there's no experimental data to compare with. Maybe they're the same thing. Some of these error bars look really big, but actually chemical accuracy is down here, 1.6. So we're getting really good results. And that was a bit of a surprise to me, actually, that we could do that. It learns the cusps, as I said. Here are the same cusp picture for a helium atom. This was when all the three particles are constrained to be on a line, and we move one electron along the line, and you see the cusps. And this is when the electron goes around a circle. And it learns the cusp conditions. This should be -2, and this should be 0.5. And it learns them really quite accurately. Because we're doing VMC, one of the things I don't like about DMC is the problem with estimators. There is no problem with estimators in VMC. If you can write it down and evaluate h psi over psi, or operator psi over psi, you can evaluate it. So this was just an example to make a picture, really, because there's too many. Okay, so now let's go on to molecules. This is to answer Sandeep's question. Can we get chemical accuracy? Not really. This is chemical accuracy, this little bar down here. And as the molecules get bigger, we're going from lithium hydride to bicyclobutane here. This is about 30 electrons. The errors are rising. If we, however, look at believe we're solid-state physicists and look at the error per electron, it's not really rising, honestly. So that's quite encouraging. It doesn't tell us, we don't know whether it scales properly, whether it's extensive, but it's looking reasonable. So we can't get there, but these are a couple clusters of all kinds. Again, we believe done well. Some of them were done by us. I think some were from the literature. It's a long time ago. And the interesting thing is our errors are there, but they seem to be smoother, less dependent on which molecule we're looking at, dependent more just on the size of the system. And we don't get these nasty jumping around. You know, ozone isn't particularly hard for us. It does seem to be hard for couple cluster. So it's quite encouraging, actually.
These all single determinants?
No, I don't think so.
Fermi Net results?
No, all the Fermi Net results I'm showing you now are 16 determinants. The couple cluster, well, it's not determinants, yeah, but these are big calculations. When I show you VMC and DMC and compare them with Fermi Net, they're usually done with lots of determinants. I think that some of the ones with Priyanka where I was adding determinants were done with many, many configuration state functions, yeah.
What's the green line right above Fermi? They just
It's couple cluster singles, doubles, and triples with an org CC PC CV5Z basis set, 5Z basis set. I think it's hard to go beyond there. That's why it doesn't go beyond there. Yeah, sorry, some of these slides are a bit small.
So one thing that we found is that if you extrapolate, that you can extrapolate pretty well between quadruples and double basis sets, and you get, with our benchmark, you could get within better than a millihartree from exact results.
You can, of course, you know, when I say there's an exact result, that's because some clever quantum chemist figured out how to do it, often with a kind of extrapolation method, or all the conventional quantum chemistry methods need an extrapolation to the complete basis set limit. That will come back later, actually. So I just wanted to reinforce how hard quantum chemistry is. This is the mean field energy, typically like 99.5% of the total energy. This little green bit is the correlation energy, so I blew it up here. This is our error, typically, in these things. So, you know, 99.95% of the correlation energy, these are for various of these molecules. Bicyclobutane we had more trouble with. I'm not sure why. We never really went back to try and see how well we could do on that. But it's a really nasty problem because of this range of energy scales. We can pull atoms apart, pull molecules apart. That works quite well. This is pulling apart nitrogen. Various methods here. I don't even know what they are. This is some kind of couple cluster. Again, the story is that they all have a bit, well, the couple cluster and us both have a bit of trouble when the bond is breaking, but we're comparable. You know, it's not perfect, but it's not terrible either, and it's just variational Monte Carlo. Like Frank's group, we went back and looked at this H10 benchmark by Motta from the Simons collaboration. And we just took their numbers. This is basically all of the good numbers from that paper, and just added one line, which is the Fermi Net one, which is the golden one here. And you can see Fermi Net is actually, this green region is where the collaboration doing this thought the right answer probably was. And Fermi Net is doing really well, doing better than VMC of conventional kinds. And it's up there with auxiliary field Monte Carlo, which was very consistently good here. Diffusion Monte Carlo is not on here because it was very similar to auxiliary field Monte Carlo in this particular paper, and it just made too complicated a figure. Again, we're just repeating things you heard yesterday. Yeah, we looked at the bicyclobutane-butadiene transformation and calculated the energies of all the states in between. The interesting thing here is just how similar our results are to diffusion Monte Carlo. They differ more from different kinds of coupled cluster, but they really are very consistent with diffusion Monte Carlo. And where there are experimental results, this one is perfectly in line. This one may be a little bit out of line. Who knows where the error is, yeah.
In DMC, do you remember what kind of ansatz they had? Like,
Okay, it was I don't remember who did it. I think it was a multi-determinant Slater-Jastrow.
Yeah.
But I don't remember the details, I'm afraid. But, I mean, the thing is that...
Because that's limited by the nodal surface.
Yeah,
right?
yeah. But, I mean, you optimize the linear combination, yes.
So your results are with or without the pseudopotential?
We don't have any pseudopotentials here yet.
But the DMC does.
The DMC probably did, yes. Yeah.
Some calculations I did, the pseudopotential uncertainty was reasonably high for something like benzene or something.
All I can say here is we do not have pseudopotentials in this, and we agree with that DMC. So I should check who did that DMC. I should go back, because it's a long time since I made this slide, and I'm sorry, I've forgotten. One of the nice things about this, about having such a dumb method, is that there's not a lot of smart stuff went into it, except building the neural network in the first place. So if you want to do something different where you're starting again, you don't have to rebuild all the smart stuff, you just do it. So Gino was reading one day about positrons and how they stick to molecules, which is a topic of some interest in chemistry now because they can measure positron binding energies. And he thought, let's just add a positron to Fermi Net, I'll just put in another stream. And he literally did it overnight and was getting answers the next day. And they're very good. Our affinity, Fermi Net affinity, this is called explicitly correlated Gaussian. It's supposed to be accurate for very tiny systems. We agree with it nicely. In this one, we agree quite nicely with Dario Bressanini's old diffusion Monte Carlo work as well. So we haven't really pursued this very much. Gino did one more, because he went on to other things, he did one more molecule, which was beryllium oxide. And there are much more interesting things to do here. Here our affinity came out to 0.0151 Hartrees. And Dario's old one was nearly twice as big. And we never really understand why. We did find one more method capable of doing this, which I didn't understand how it works in detail, and I didn't completely trust it. Maybe some of you know how it works. And that agreed more or less with us, but I'd say this one is still a bit open, actually. I think we're the right answer, but I would. So we haven't pursued this, but there's a lot we can do with this, I think. And you can imagine, putting mu on, doing mu-SR calculations and things, so interesting things. You could, of course, use a Fermi Net as a base for diffusion Monte Carlo, and do diffusion Monte Carlo on top. We tried that. So did other people. Max Wilson is an interesting guy. He was at the time a PhD student, not with a physics or chemistry background, and he took our Fermi Net code, which is open source, and built his own, essentially. I mean, he was reading ours, but he wrote his own Fermi Net code all on his own, and then he put DMC in as well, and got there slightly before us. This is a repeated story, I'm afraid. I have new PhD students, and when they're competing against people at postdoc, who are at postdoc level and things, they keep getting scooped. So this was one scoopage, and then, but let's show the results we got. What Max got similar conclusions. This was ethanol. This is coupled cluster singles, doubles, and triples. We get lower energies than that, but not when you extrapolate the coupled cluster to the complete basis set limit. Then that gets a lower energy. So if we take this as the true answer, you can see that the addition of diffusion Monte Carlo gets us from 0.0308 down to 0.037, and we've got to go all the way to 0.054. So it's not a very big improvement, 30%, something like that. That disappointed me. I was expecting 80%. So I was expecting to have essentially perfect results. The same story for other molecules. This is all we did with this, because we got scooped by Max, and Gino went off the idea of trying to write a paper on DMC. very recently, there's also a team at ByteDance. This is the company behind TikTok. So TikTok is doing quantum physics now, where they've got quite a large team, several people, postdoc level kind of people, working on this, and they're using the FermiNet code, but they're good engineers and they have good computing resources, and they're doing a lot. And very recently, this paper came out, which did a lot of diffusion Monte Carlo and a lot more interesting and different things. They have a slightly more positive, they have a much more positive story. But if you look at the numbers, the truth of how negative to be is somewhere between us and them, I think. They did things like doing intentionally bad variational optimizations and then saying, oh, look, DMC gains us more then. And the argument was that you can then do it quicker because optimization is very slow. So it's well worth seeing. This just came out on the archive very recently. But our conclusion on DMC is that we would rather, for the time being, stick with VMC. Yeah.
It might kind of depend on whether the model surface converges faster than the energy fast, then it might make sense to have the implementation sooner than VMC.
Yeah. I mean, I think the story here is, at least for these simple molecules, our description of the nodal surface is what it is. But between the nodes, our wave function is almost perfect because DMC gains us so little extra. But we're not really fixing the nodes as much as we would hope. Periodic boundary conditions is what because I'm more interested in. How long have I got? Oh, not very long. Okay. Because that's my background. I've never worked on molecules until I did this project. So let's just think of a very simple example, how you do periodic boundary conditions. We want the wave function, which is the output of the neural network, to be a periodic function of the electron positions, which are inputs. Okay, so if R is the box in which the electrons are being simulated, you can imagine a periodic repetition of that if you want. And this is a lattice vector of that lattice of boxes. We want to say that if we pick up any electron and move it right along out of the box into the same position in the next box, or equivalently round the periodic boundary conditions back to where it started, we want the wave function to remain unaltered. We can easily put a twist in here as well. There's no difficulty with twists in principle. The easiest way to do this, not our idea, is to just replace each of the inputs Ri, and we have to do the same with remember we're using modulus of these vectors as inputs too. Replace the inputs by a smooth periodic function of themselves. So if, when we pick up an electron and move it along one box, the periodic function remains it goes back to the starting value. All the inputs to the neural network are back to where they were as well. The neural network cannot tell. It must be periodic, no matter, we don't have to constrain it. And so one way to do this, which is the conventional way, if you have an input vector I, you just expand it in terms of the primitive vectors of this lattice of supercells. These coordinates we can choose between 0 and 1. And then instead of putting in R, or equivalently S1, S2, and S3 to our neural network, we put in sines and cosines of them. So these are naturally periodic. This is a well-known idea. It's a bit funny that we started with 3 coordinates and we now have to put in 6. But if you just put in 3, say, just think of a 1D example. If we just put in sine 2 pi x, it goes, as we go through the unit cell, it does that. And there are 2 places where it's 0, and we can't distinguish them from that. So this is why we put in both of them. Other people do it too. Some weird topological reason, which I can't explain, but I can see. We had more trouble with a periodic analog of the distance. That's a bit harder. You want various constraints. When two electrons, let's say we just have an electron approaching the origin and we want to measure the distance from the origin. When it approaches the origin, we want that distance to reduce to the Euclidean distance. And we want it to be spherical so that surfaces of constant distance from the origin are true spheres in R space, in the real space. After a lot of fiddling around one wet Sunday afternoon, I came up with this. I can't quite remember how I got there, but it came from Rester's ideas about periodic definitions of position vectors. And this satisfies that constraint. It's periodic. It looks exactly like the Euclidean norm as you approach the origin. It's spherical around the origin to leading order. The simpler choice, which had often been used before, is this. That is actually, when you go close to the origin, it's not spherical, unless you're in a cubic system. So we prefer our one, even though it's a little bit more complicated. But we've used both. We get the same answers, actually, nearly the same answers. So that's all you have to do to make the system periodic. If you want to put a twist in, you add an explicit phase factor. Because the twisted wave function can be written by a phase factor as a phase factor multiplied by a periodic function. And we essentially fit the periodic function. So here's the uniform electron gas for 14 electrons, where we were also scooped by Max Wilson. With Saverio, he now got together with people who know about electrons, Saverio and Marcus. That helped him. But we both did this 14 electron system, got similar results. And we did this system because there's very accurate initiator FCI QMC data for it. That's why we did it. And all I want to show really is this is a DMC. This is one determinant DMC, but with backflow, so done quite nicely. If you look at it, compare it with FermiNet, is it one determinant DMC? I should check that. Actually, I think it isn't, because these DMC results were taken from this paper, and they got Pablo to do a really good DMC for that, so I suspect it's multi-determinant DMC. Does anyone remember? No. Okay, I'm sorry. Anyway, FermiNet is very, very close to DMC. That's the conclusion here. But they're both still some way from the finite basis set limit. But all these numbers are really, really good, is the short story. So it works very, very well for this. We then went on to do something a bit more interesting. I'm going to rush a bit and get through in about 5 to 6 minutes. Electrons in solids act in many ways like a liquid most of the time. We talk about the Fermi liquid. But if you make the solid very low density, the Coulomb interactions dominate over the kinetic energy, it turns out, and the electronic liquid will crystallize. This is completely in the absence of atoms, so there are no nuclei, it's just a uniform positive background, and if the density gets low enough, the electrons crystallize. And that's called a Wigner crystal. It's never been seen in 3D. But it has been seen in lower dimensions, because we don't really have many solids without nuclei in. It's a kind of funny crystal, and even we don't in 2D either, but they've done it in kind of 2 eggs. It's a funny kind of crystal in that the electron density, at least for small systems, remains uniform. And you see the crystalline order in the pair correlation function. So if there's an electron here, you're more likely to find other electrons on a lattice. But that first electron is equally likely to be anywhere. Okay. In small systems, that's the true ground state. If there's a very small perturbation, however, it's quite easy to localize the crystal and make that density appear in the 1 electron density. Actually, what you're doing is localizing the center of mass, and that becomes easier and easier and easier as the number of electrons increases. So real Wigner crystals, if they were to be found, would exist somewhere. They wouldn't be this complicated superposition. And Wigner crystallization, where it actually appears somewhere, was recently imaged for the first time in 2D. This is not the image, this is a cartoon of mushrooms growing on an atomic surface, but it was something like that. Continuum quantum Monte Carlo methods like VMC and DMC, I think it's fair to say, not good at finding phase transitions. It's hard to do. I'll show you how you do it here, in this example, in a minute. But the nice thing about FermiNet is we spontaneously found a 3D Wigner crystal. I'll explain all the limitations in a second, yeah? So this is just the advertisement. This is at 1 RS, where you can see a faint crystalline order appearing. And this is at a much lower RS, where the crystal becomes much more pronounced. Okay?
We see this easily in path intervals.
Yeah, you do in path intervals, that's true, yeah.
Even in zero temperature path intervals.
Okay, I didn't know that, actually. Actually, I didn't know you could see it at all with path integrals. But again, it's one of these methods where you don't put anything in. Could you do it with fermions, though?
Yeah, we have done it.
With the fixed path, fixed boundary on the path, it still works.
Right.
Okay, that does surprise me. Okay. So this system was too small, way too small. It was 27 electrons in a body-centered cubic simulation cell, and we didn't do twist averaging for reasons I'll explain in a minute. The simulation cell is far too small to get anywhere near the right answer. Yeah, the true density is much, much lower at which this transition appears, especially without twist averaging. And because we put the 3 by 3 by 3 body-centered cubic cells in a box, just right for the 27 electrons to organize in a 3 by 3 by 3 lattice, that vastly favors the crystalline state. So it's not physics. Well, it's not the right answer. Okay, I can do it. But it's not the right answer, but we can compare with, if we compare with Slater-Jastrow backflow, VMC and DMC for the same simulation cell, that's a valid comparison. So that's at least something we can do, and we did that. So here, for example, if you want to do this transition with VMC, for example, you have to choose different trial wave functions for the crystal and for the liquid states. And here's the crystalline trial wave function, and this is the ground state energy calculated with that trial wave function as a function of RS. So it's smooth. So at high RS, it's a bad wave function, and at low RS, it's a good wave function. Is that right? This is the crystal. Yeah. And you can also take the gas wave function. What we're not plotting energy here. This is the order parameter. So this is the amount of crystallinity. If you take the liquid wave function, of course, there's no order anywhere. And what you have to do then is you have to calculate the energies for all of these red points and all of this blue line and see which is winning at any density, which energy is lower, and compare the two. And you get that. FermiNet gave you the black ones, which you can see really does see a clear transition here, even in such a tiny system. The proof is in the energies. These are energies relative to the FermiNet energy. So anything positive means that FermiNet is lower and is doing better. So over here, at high density, FermiNet is beating everything, essentially. At low density, at very low density, the very best calculations are actually done with a DMC crystalline wave function, which is slightly better than FermiNet, but very little different. And if you're doing a conventional DMC to see where the transition is, you look where the bluish curves cross the reddish ones. Okay, all of this has been a bit of a con in that all of these densities I showed you were 1 electron densities, and I said it should be a floating crystal, which is this superposition of 1 electron density crystals everywhere. We don't get that. DMC puts it in as being a 1 electron crystal already in the trial wave function. However, we can get it in FermiNet if we just switch off the 1 electron inputs. The architecture of the network is the same, but we don't put in the electron positions. We only put in electron spacings. Obviously, then you can't get the crystal in the 1 electron density, but we do still see it. This is an element of the structure factor, which measures a Fourier component of this 2 electron density. So it's still there. Okay, I think I'd better really rush. We can do pseudopotentials. Okay, I thought the biggest problem we have is going to large systems. It's just too slow and painful, and optimization takes forever. So we thought maybe pseudopotentials would help. And of course it does help. It gets rid of a lot of electrons. But because we don't have a rank 1 update formula, we can't take advantage of moving electrons one by one because every element of our determinant depends on the position of every electron. It's actually not a great saving in time except for the reduction in the electron number. But all there is to say here is it works fine. And pseudopotentials work fine, and we have some pseudopotential calculations. I'm skipping this. We've also just started looking at solids. Again, we've been somewhat scooped by the ByteDance people who've done quite a lot of work on solids with similar results. So this is Halvard's work, who also did the pseudopotentials work. So what we've got here is a very tiny simulation cell. This is a not particularly good DMC simulation. It's just regular one-determinant Slater-Jastrow DMC. We haven't done backflow. We haven't done multi-determinant here. But you can see that FermiNet is doing pretty well here, getting down to answers significantly below the one-core DMC, the one-determinant DMC. And so this was full core. This is pseudopotential, and it's the same story. So we can do solids. We can scale up only at the moment reasonably on the resources we have available to about 40 electrons, 50 electrons. Going beyond that gets just too painful. So that means that, in my view, that's not really enough to do solids, which is a great frustration to me. But the fact that we can see phase transitions is interesting, and we might be able to see more interesting ones. That's what we're looking at the moment. We've done some slightly bigger ones as well, very similar to the ByteDance data. We do very slightly better than them. We can do twisted boundary conditions, and it works fine in insulators. For some reason in metals, when we're optimizing with a twist, we don't get very good results. We have not got to the bottom of this. So we can do DMC at the gamma point, and we beat it, And then away from the gamma point, it beats us by about the same amount. It's really frustrating. It's not something we understand. But anyway, it happens. And that's all. Thank you very much. Sorry about going on too long.